Thank you so much. So, yeah, I'm with Zenseact, and I'm going to talk about how we're going to scale our stack to face all of the challenges in autonomous driving. So first, a little bit about Zenseact. So we're an autonomous driving company. We're a subsidiary of Volvo Cars, and you can find our software in Polestar and Volvo vehicles. Our motto is towards zero faster, and that's because every year there's 1.2 million deaths in traffic and more than 50 million injuries, and we believe that automation is the way to bring those numbers to zero as quickly as possible. To automate driving, we equip our cars with many sensors. So there's several cameras, 7 of them in fact. There's 1 looking forward, 2 cameras looking backwards, and then 4 surround cameras with a wide viewing angle. Then we have 1 forward-looking LiDAR and radars covering all the angles around the car. The reason for using multiple sensors is that they give complementary information, like a LiDAR tells you how far something is in 3D space, and it increases safety. For instance, LiDARs and radars are active sensors, so they can see perfectly in the dark. A radar can see through fog, which, for instance, a camera cannot. But having these sensors is one thing. Actually using them in an optimal way to build a perception system is surprisingly difficult. And this brings me to the transition we're undergoing at Zenseact towards an end-to-end autonomous driving system. On top, you can see basically how our current stack looks, the one that's in the Polestar or the EX90, and how almost any autonomous driving system today works. You have a bunch of sensors, maybe a map, and then your deep learning model really just sees 1 sensor at a time and typically just 1 snapshot of it. If we look at the scene in the bottom here, 1 sensor would be a camera, for instance, and 1 snapshot in the camera is just a single image. And then in this image, you would detect some cars, maybe these red ones, with your deep learning model. And then you send all of these snapshots you get from your single sensors into a system of human-designed algorithms that combine this information into a view of what's happening in the world around you. And then you try to forecast how other people are going to behave in traffic, and finally you plan your own trajectory, which is this yellow line here. We believe that this is actually not going to scale to all of the challenges faced in autonomous driving, so we're transitioning towards this. A true end-to-end system where we stream all of our sensors into 1 big deep learning model that reasons about the evolution of the environment and how everyone will behave in it. And it even outputs a plan, so it proposes a plan. This yellow line could come straight out of our deep learning model. But then we still add some safety guardrails there, so that's why there's still some classical algorithms in the planning. I'll walk you through at a high level how this end-to-end autonomous driving system really works. So the core of it all is what we call a neural world representation. This is really just a large blob of numbers that, to our neural network, represent the world around it and what it knows about that world. But it's not human interpretable. Then we have a lot of sensors. We have our cameras, radars, LiDARs, and even information about how our own car is driving. And then we feed all of it to the neural network. And it combines all of this new sensor data with what it already knows about the world to generate a new neural world representation. So basically, what it already knew and new sensor data get fused into a new view of the world. And then we can decode that into human interpretable form, like object trajectories, the structure of the road, and proposing a plan for how to drive. The real system is actually a little bit more complicated than that. To ensure safety, we divide our sensors into 2 separate clusters with a separate computer. And on each of these clusters, we apply exactly the same principles. So we have a neural world representation. Our model fuses new sensor information into it to get a new view of the world. And finally, we merge these 2 world views into 1 final representation that we use to operate our system. If anything fails, we can still fall back to 1 of the clusters and still operate the car safely. Okay, this design looks great, and end-to-end autonomous driving sounds very attractive. But there is really 1 critical thing in all of this, and that's the data. Deep learning models only work in environments they're familiar with, which means that you have training data representing this environment. To show you what kind of challenges this holds, I have 1 scene here that's actually in our dataset. So this is a Zenseact data collection vehicle driving under the Aurora. If you have never seen a scene like this, and a customer vehicle would face it, your stack is probably going to fail here. So you need a very good pipeline to efficiently collect and gather and analyze data at scale. But it's more important than ever when building an end-to-end system, because now, without any human algorithms in the system, you don't have any knobs to turn, you don't have any buttons to push if anything goes wrong. The only thing you can do if customers complain is to gather more data that represents those failure cases. And when gathering data and building our data set, there is a critical bottleneck, and that's manual labeling. In our legacy system, we used single snapshots of a single sensor, so like a camera image. And then you could send a lot of those to a human labeling company. They would just have their human labelers, draw boxes around cars, mark where the lane lines are, and so on. And then with a lot of that data, you can train your own deep learning models to essentially imitate that, to detect objects or where the road is. Our new perception system doesn't reason about a single snapshot in time, it reasons about the evolution of the world around it. So it also needs a sequence of data that spans more than a few seconds. So we actually use 10-second sequences of data from all our sensors as a single training sample. So now a single training sample for our neural network actually contains about 1,000 images. You have 7 cameras, each giving 15 images per second, and 100 point clouds. If you could label, or to put it into perspective, if you could label an image a minute and you worked 8 hours per day, labeling the data set we built last year would take you about 6,000 years. So it's incredibly labor-intensive to make a data set for this kind of end-to-end model, and we believe this will be a bottleneck to our progress. So we're going towards auto-labeling. The principle is quite simple. Normally, you would have a group of human labelers, and you give them data, and then you get these boxes around your vehicles, in this case, which is the labels, and then your model learns from this. We want to replace that with a neural network-based system. So we want to give this data to a big neural network that then also solves the labels on which we can train our in-car system. But then you might ask the question, if you can automate the labeling process, why would you need labels in the first place? And it's a valid question, but when making an auto-labeling system, we have several advantages compared to a system that we deploy in car. First of all, we can use much larger amounts of compute. I'll dig into that soon. We also don't have to give the answer in real time. Imagine you're driving and a child jumps in front of your car. You don't want the car to think for 30 minutes whether it's actually a child in front of it. You want it to react immediately. When auto-labeling the same scene, it could be fine if it takes half an hour, as long as the answer is as correct as possible. And finally, we can look both forward and backward in time for data we have already collected. But let's dig into computation a little bit more and how we can use compute to make auto-labeling happen. And to illustrate that, I want to show a very famous plot from research on large language models because it applies to any field of deep learning, essentially. What you see here is the loss function, which measures how smart the model is, essentially. The lower this value, the better the model is or the smarter it is. And then you see the number of training data it was used to train the models, but more importantly, also models of different sizes. So in this case, the yellow model and the green model are much bigger than, for instance, the blue and the purple ones. And what you see is that bigger models are just smarter. They're essentially better at any task you give them. And this is one of the main challenges in autonomous driving, because everything we do has to react instantaneously and run everywhere, so it has to work in car on one of these small machines. This is an NVIDIA Orin, and it's what's deployed, for instance, in the Volvo EX90, but it's very, very small compared to the computers you would run a large language model on, which looks more like something like this. But for auto-labeling, we can go exactly the same way. We can also train very large models and run it on very big clusters, as long as the answer is good. But then we're faced with a chicken and egg problem. If we're going to make a big model that does the labeling for us, where do we get the labels for that model from? And the answer lies in self-supervised learning. The concept is quite easy. I try to illustrate it here. Imagine you have a video that's 10 seconds long. You could take the first 5 seconds of this video, and you could give it as an input to your model. And based on those 5 seconds of video, you could ask your model to predict the next 5 seconds of the video. That's what's shown here. The blue is what you would give the model, the orange is what it needs to predict. Alternatively, you could remove a few seconds here and there and ask your model to fill in the blanks. To understand why this works, I want to show you this scene here. So this is a quite complicated intersection. There's a lot of cars, there's a bunch of traffic lights, and so on. But if you close your eyes for a moment, you can actually picture very well how this scene is going to evolve. You know that those two cars in front of us, they're probably going to drive ahead. Some other cars are going to turn to the right. Once the traffic lights here change color, cars are going to come from the other directions. So you can predict the future in a scene like this relatively well. And it's because you understand all of the concepts in the scene. You understand what a car is, you understand what the road is, you understand the rules of traffic. Well, it turns out that if we train a neural network on vast amounts of data and force it to predict the future, it's also forced to learn all of these concepts. It can't predict the future without knowing what a car is in this scene. So we tried it out, and recently Zenseact published a paper, and it's mainly the work of our amazing PhD students, which tries just this, predicting the future and seeing how we can leverage that model for downstream tasks. So what was done in this paper is predicting the future in 3 particular ways. The first is predicting future occupancy. It's essentially just answering questions like, this point 10 meters in front of me, is there going to be something there 1 second from now? What about 2 seconds from now? And what about this point to the right of me? Is there going to be something there? Then we're also predicting the future flow of visual information, as well as the trajectory our own car is driving. The model, it looks a little bit complicated, but essentially we just take some past data, we run it through the model here in yellow, and we get a neural representation. And then we ask a lot of questions to this neural representation. Before going into quantitative results, let's look into the mind's eye of this model a little bit. So the video I'm going to show here is a little bit abstract, but it's essentially predicted neural features from our model. So these are not meant to be human interpretable, but we can still visualize them as scholars to get some idea of what this model is seeing. So here you see it's driving around. And what you can notice is that it clearly understands the concept of cars because they appear as a distinct different color. It also knows where the road is because the road also has a different color in its neural representation. So it definitely knows something about the world. But can we actually use something like this for labeling? And the answer is yes. So to study that, after training this model, it was also fine-tuned on labeled data. So what you see here is the precision of the model in detecting objects 3 seconds into the future as a function of the number of labeled training samples. So here you have some human labels. And then you see the model trained at Zenseact in green against the previous best model in blue, or the previous best in the literature, and then some other models from the literature. And the result is quite amazing. It's better than anything before, but in particular with just a single labeled training sample, it can detect almost 50% of objects correctly. So this looks really good. But then what's also important is if you give it more and more pre-training samples, so this is unlabeled samples, so you're asking it to predict the future on more and more and more data. It turns out that its performance on things like object detection, which is in this case shown in blue, keeps steadily increasing the more data you train this kind of model on. So that sounds great. We just need to give it more data, and we need to put more compute in it to make it a bigger model, and then we should have a pretty good auto-labeling system. And this is exactly what we want to do. And this is one of the reasons why in Zenseact we recently built a new deep learning cluster. And this is possibly the largest single company-owned GPU supercomputer in the Nordics right now. It consists mainly of DGX H100s with some DGX A100s as well. It is a direct InfiniBand link to Volvo's data center so that we can pre-train our models on massive amounts of data. But even though it's a large cluster here in the Nordics, it's still relatively modest to what you would see for LLM trainings. And the reason is partially that we also believe that the compute of our cluster should also still be fundamentally linked to what we have in cars, which is this small NVIDIA Orin. At some point, getting more compute in your cluster won't help you anymore. So we want to pre-train models. We have a lot of compute to scale it up, both in the data and in the model size. And with that, we want to make an auto-labeling system. So let's see what our current auto-labeling system actually looks like. Before starting the video, I'll walk you through it. So we see a representation of our own car in blue. And then you see it detect all of the other traffic participants, and here a large parking lot with a lot of cars. So I'll let it play now. So you can see that the detections are very consistent and very smooth in time, and it doesn't seem to miss anything. So here you can see how crisp the bounding boxes look. And then we can also actually zoom in on one particular detection here just to give a sense of how precise the auto-labeling is. So here you see one truck. You can see a top view, a side view, and a rear view, so you can see that this bounding box is really precise. Okay, looks good. Is this actually good enough to train a model? Let's see. So here I will show you a video of our current production build of our next generation deep learning system, but with a twist. This model is trained with 0 manual annotations. I'll play the video twice. I'll start it and walk you through it while it's playing. So on top, you can see the trajectory prediction. So it's proposing a plan of how we should drive. And what you should note is that when there's multiple options, the model understands it. It will predict multiple possible trajectories. Then in the second view, you see object detections in the forward camera, which again is trained without any labels. So you can see that it's detecting objects very well. There will be some complicated crossings when I play the video again, where you see that it's detecting almost everything. And then you can also see the detections in the LiDAR, radars, and all of the side cameras and so on. So here you could see this multimodal trajectory predictions, for instance. So let's go back to the same video, now that you know what you're actually looking at. So again, look at the detections. Like, these look quite stable and good. They're not perfect, of course, but here at high speed, you can see it detect everything. Here is a complicated crossing with a lot of cars and parked cars. It's basically detecting it all, and everything without a single label. Then this brings me to my conclusions now at the end. So in Zenseact, we're transitioning from a more traditional autonomous driving stack, which is based on models seeing one sensor at one snapshot in time, to a full end-to-end system that does sensor fusion, tracking, forecasting, and finally even proposes plans. To do this, we need to really scale our data set and do it efficiently, so we want to go all in with as few manual labels as possible, so we need to auto-label. And we believe that the way to auto-label is to train large self-supervised models. So we're essentially trading human labor for compute when doing this. And we're just in the beginning of this journey, so we plan to train far larger and better models as time goes. And to do all this, both to train our new end-to-end deep learning stack and to train these large auto-labeling models, we built a large new deep learning supercomputer that based on DGX H100 and A100 nodes. Thank you very much for listening.
Thank you so much, Willem. This was super interesting. And I actually, so abruptly here, I would like to ask you something super quickly.
Absolutely.
So because you're saying you're still in the beginning of your journey and therefore it's still in the experimental phase, I would love you must share some failing story, or not failing, but like surprise or friction point that there was in this shift. And for me, it can be either technical or even cultural.
Yeah, I don't have any funny stories to share, but I think the biggest problem was building the data set. I mean, in the past, we could get away with one camera working or a few cameras working. Now everything has to work at the same time to get one training sample, and setting up that entire pipeline was quite challenging.
But do you think it's also a cultural shift to move from,
Absolutely. I mean, a lot of engineers in our company are also making the transition now towards getting more and more into deep learning, as it's eating the stack, essentially, as we migrate from classical algorithms to a deep learning-based system.
Thank you very much. Yeah. Okay, I promise now the audience can ask questions as well. Yes, we have a hand raised there.
Thank you for interesting work that you have done. I have heard that you have mentioned several times that LLM models. I'm just wondering that it is the LLM models or the VLM models?
We're not using any LLM models in anything I showed here.
Okay, how about the VLM models?
Oh, no, we're not either. But I mean, we use VLM models, for instance, to search data because models like CLIP are very efficient ways to, parse a lot of raw data. But all the models I showed here are models we trained from scratch within Zenseact.
Thank you.
Thank you very much. Another question here.
Go ahead.
Thank you. Very interesting project. My question is, when you are driving as human driver, you're not really paying attention everything in a road, even when sometimes we should.
Yeah.
My question here is, I saw that some part of the video are not labeled, some objects that were not regular. Do you have a minimum threshold to consider, well, this labeling is acceptable to incorporate in your final model?
Yeah, I mean, so the video is definitely not perfect, and the reason for that is that we're quite early in this auto-labeling journey, and there's no reason we would use absolutely zero manual labels to make the final product, because, I mean, we have to be realistic. This was just a demo to show it here. So the current model, if we train it even just a little bit longer, it would do quite a lot better. But, I mean, in the end, we want it to be absolutely safe, so we want to miss nothing under any circumstance if we can.
Thank you very much. Do we have another question for Willem? Yes.
Hello. How much safer than human driving are you at about now? And where do you think we'll actually start convince people to let go? Because that's the human...
I mean, it's a very good question. I mean, I'm not an expert on, let's say, legislation and when you can turn on fully autonomous systems. But our current stack is deployed in the Polestar 3 and the EX90, and it's already operational. It's just that, okay, you can't take your hands off, but let's say someone would jump in front of your car, it would almost for sure detect it and brake the car and, save a life in that case. So it's operational, it's helping drivers at the moment, but yeah, it's not in a state where you could just take your hands off, fall asleep, and assume you arrive safely at your destination, let's say.
Thank you.
Hello, thank you for a wonderful presentation. It looks fantastic, really. And my question is, you mentioned that you are transitioning from one image to like batch of 10 seconds. And I'm wondering, you are trying to predict like planned behavior, but as you mentioned, what if something super unexpected happens, someone jumped just before the car? So how good are the models in that situation? Or should you rely on different techniques like?
Yeah, so if I'll quickly go back in the slides to, so this is why it's essential that there's actually still some human written logic here, why I had it, in both red and green. Because currently our planning proposals come from imitation learning. So it's basically seeing how the human driver drove and it learns to imitate that behavior. But our data set doesn't contain any possible, every possible scenario you might ever encounter. So if something extreme happens and we detect an object jumping in front of us, then we would cross-check our plan with what comes out of the object detector and so on.
Yes, sounds reasonable. Thank you.
Thank you very much. We have time for one short question. In the meantime, people who are standing, if you would like to take a seat, I think you will not disturb anybody in this moment.
There's someone there that wants to ask a question. Oh, okay.
Hello, thank you for a very good presentation. I have a question. I think with LiDAR there is a lot of ghost items that appear when the LiDAR detecting. How is it going with the in that case?
But what do you mean by ghost? So that there is
something that is
false positives or errors in the LiDAR, because it's quite a different. Like I think you mean this.
When LiDAR is detect something which is not there.
Yeah. Okay. So in this scene, there's nothing being detected that's not there. I mean, it can happen, of course. So one of the things we're doing is also our auto-labeling system. At the moment, it's LiDAR-based. We're going to use more sensors in case the LiDAR point cloud becomes too sparse.
Mm-hmm. Okay.
Yeah.
Okay, thanks.
But yeah, it's also, at some point, this system doesn't have to be completely perfect also to train a good model in car. I think that's also an important thing to note, because your system in car is quite limited in compute and so on, whereas this can see extremely far in all directions with a very powerful reference LiDAR.
Yeah, I was more wondering, is there a way to clean up those kind of data or a way to compare the LiDAR with radar.
Yeah.
Yeah.
Yeah, so we don't want to explicitly compare sensors because then you're back at square one. So we want to feed all of it to one model end to end. But of course, in an auto-labeling system, we can use all the compute and time we need. So we can definitely post-process and track these outputs and look at them further as, to just make the result as crisp as possible.
Okay, thank you.
Thank you very much. And I believe we have exhausted the time for the questions. Thank you. And please accept some flowers from us. An applause to Willem Verbeke.